All right, hey everyone. Today we're going to be talking about geometric sequences and also geometric series. I just want to start with a little review of what we know about arithmetic sequences and series. So for arithmetic, we know that, for example, we could have the sequence, I don't know, 3, let's make it simple, 3, 5, 7, 9, etc., etc. So the important things are the first term. So they like u in IB. So u1 here is 3, and then d for the common difference in this case is 2, because we're adding 2 every time. Added 2 every time we get to the next term. And the first thing that we learned was to figure out the formula for un. This is in your formula booklet. It's just u1 plus n minus 1 times d. And the reason for that is because the first term you haven't added anything yet, and then you add it once, and then you've added twice, right? And that keeps going. So the nth term, right? The first term you haven't added it at all. The second term you've added it once. Then the third term you've added it twice. It's always n minus 1, right? So this formula was the first one we learned. And then, so in this case, I guess the example up here that I had, it would be un would be equal to 3 plus n minus 1 times 2. And you can always distribute the 2. That would give you what? 1 plus 3n. Is that right? 3 minus 2 is 1. 1 plus 2n, sorry. It's like that's not right. There you go. Okay, so you could simplify or you can leave it like that either way. And then we proved using kind of the Freddy-Gauss method that if you want to add the first n terms together, you can do n over 2 times u1 plus un. So the first term and the last term in the series that you want to add together. Or another way to write that is n over 2 times 2u1 plus n minus 1 times d. And it just depends on what you know, which formula you're going to use. And those formulas are all in your formula booklet. And the goal today is going to be to do the same thing, but with a geometric sequence and series. So we're going to say, how do we get un for geo? And how do we get Sn for a geometric sequence or series? So remember, for a geometric, just a reminder, it's where you're multiplying every time. So a geometric sequence, it could look like this. For example, we could have, I don't know, 4, 8, 16, 32, 64. In that case, our first term is 4, and our common ratio r is 2, because we're doubling every time, right? You're multiplying by r each time to get to the next term. Another one, you could do one where you're dividing instead. Try to think of something that would work out pretty well here. You could do like 81, 27, 9, 3, 1/3, 1/9, etc., etc. In this case, our first term would be 81, and our common ratio is 1/3. So, figuring out how this guy works, right? It's very similar to actually kind of this idea for an arithmetic. And I'm just going to kind of write it in the corner here, and then we'll try this problem in a second. But to get the nth term, right? So if we look at it, you have u1, and then you have u1 multiplied by r, and then you have u1 multiplied by r squared, etc., right? Because you multiply by r to get the first one, and then you could think of 16 as 4 times 4, and then you can think of 32 as 4 times 8, right? You keep multiplying by r one more time. So very similar to how you add one less d than the term number you're on. It's the same thing here. The first term doesn't have any r's, the second term has one r, the third term has two r's, so it's always going to be u1 multiplied by r to the power n minus 1. That is the general formula. It's in your formula booklet for the nth term of a geometric sequence. And that is what we're going to use to find this first one. But in your note packet, this is where your note packet kind of starts. We can write down the general form for the nth term of a geometric sequence. Un is going to be u1 multiplied by r to the power n minus 1. You can put that in brackets if you want, or if it's really clear it's in the exponent, it doesn't matter. But first term multiplied by r to the n minus 1. So you plug in 1, the r doesn't matter at all because you have r to the 0, which is 1. You plug in 2, you're going to have r to the 1. 3, r squared, right? So it's always 1 less than the term number you're on. So here, they want us to find the formula for un. They give us the third term, and they also give us the sixth term. So the way I like to think about this is we have 1, 2, 3. The third term is 2.42. Then 4, 5. The sixth term is 3. Holy cow, 22102. So we don't know what u1 is. We're going to have to find that. They tell us we're going to have to find that. We're also going to have to find out what r is. And then they want us to find u21, which we'll just use our formula to find after we find it. So the way I'm going to think about this is that to get from here to here, what do? to this term right here. We're going to multiply by r, right? Then we're going to multiply by r again, and then r one more time to get to the sixth term. So you could just jump straight to the formula here that you can do, well, 3.22102 is going to have to be 2.42 multiplied by how many r's? Well, we've got one here, and one here, so r cubed. Another way to do it is say, well, this term right here is going to be 2.42r. This term here is going to be 2.42r squared. Sorry, it's getting a little bit small there. And then this term right here must be 2.42r cubed. Right? So these two have to be equal, which is exactly what the formula is that we have down here. So now we just jump to the calculator. I'm going to divide both sides by 2.42. 2.42. And we get, let me just check my calculator real quick here. Let's see. I actually have the actual entire r. Let's see what this is, though. So if I do 3.22102 divided by 2.42, sorry, you can't see my calculator. I get 1.331 equals r cubed, and then we just cube root or take it to the 1/3 power, and we get r equals 1.1. There you go. All right, so we have our r value now, and now we are going to see if we can figure out what the first term was. So if we go backwards, right, we should be able to get to here by dividing by 1.1 and then dividing by 1.1 again. So if I do 2.42 divided by 1.1, I get 2.2. And then if I divide that by 1.1, oh, I think that's going to be exactly 2. That's pretty nice. So I have my r, I have my u1, which is 2. And now I can make my formula, right? So un will just be our first term, which is 2, multiplied by our r, which is 1.1 to the power n minus 1. There we go. Now we have our formula for the nth term. So if I want u21, which is what they ask us for, to three significant figures, it's going to be 2 times 1.1 to the power of 21 minus 1, which is 20. So on my calculator, 1.1 to the power 20, and then multiplied by 2. So that gives me 13.454, and they want it to 3 sig figs. So I said 3 to 13.45, so that is approximately 13.5. There we go. All right. So down here it says, why is the exponent n minus 1? Because u1 has not been multiplied by r yet. Has not been multiplied by r. Right? The first time we multiply by r is the second term. Right? We kind of had that up here, right? The second term is the first time we multiply by r. And then the third term has 2 r's. The fourth term will have 3 r's. So it's always n minus 1. So could it be n? Only if you start at term 0. So if you say the first term is term 0, then it could be n. Sometimes you'll see that like in segment notation, they'll start at 0 instead of starting it at 1. But then let's say you want to add 10 terms together, you would have to stop it at 9. And then you could do like your u1 times r to the n, or to the I in this case, because we're using I as our index. But generally, you're going to see the n minus 1. Sometimes it can get a little confusing with like interest or with depreciation, which we're going to see in the next example. Because like if you have your principal value, that's your first term, right? And then but at the end of the first year, you're going to have your principal multiplied by your rate, and then PR squared, right? But if they say, like, how much money will you have in, let's say, 10 years? Well, in 10 years is a little weird, because if the first term, there's no R, at the end of 1 year, there's 1 R. So it's weird, because the 10th term, or the 10 years is really the 11th term, so it would be P times R to the 10. That's kind of weird as well, and that kind of also explains how you could think about it as N, and we'll see that in the next example if that didn't make sense. You'll see it in just a moment. So Costas bought a car for 16,000 euros. It is estimated that the car will depreciate by 10% each year. Depreciate means go down. So how much is left? Sometimes you'll see this formula sometimes. So if I do 1 minus 0.1, there's 90% left. So that's going to be our R value. So find the value of the car at the end of the first year. So at the end of the first year, it's going to be 16,000 multiplied by 0.9, right? Because we lose 10%. Easiest way to do that is just multiply by 0.9. And let's see, that value of the car after 1 year, if we go to the calculator, 14,400 euros. Right. So at the end of the 1 year, 14,400 euros. Now again, this is like we were just talking about, right? It's the end of the first year, but we're already multiplying by R, right? If I want the value of the car after n years, let's call it Vn, it's going to be 16,000 times 0.9 to the n. And that's weird because like the first year you haven't had any, so it's like n is 0, right? And at the end of 1 year, we're at 14,400. At the end of 2 years, you multiply by 0.9 again. If I want 5, which is part B, it's going to be 16,000 multiplied by 0.9 to the fifth. The plus 1, minus 1, like sometimes you add 1, sometimes you subtract 1. It's kind of weird, but you just have to think about the context of the problem. Like, it's gone through 5 years, so we've gone through 5 depreciation sessions, right? So it's gotten 90%ed like 5 times. So if we go to the calculator here, that gives us $9,447.84. Okay. So for letter C, calculate after how many years the value of the car falls below half its original value. Well, half of the value is 8,000, so I'm going to solve this equation. 8,000 is equal to 16,000 times 0.9 to the n or the x or whatever you want. Lots of ways to solve this. You could just graph it right away. You'd have to have a really high y value for your window. Make sure you go up to at least 8,000. The number of years, well, we're already down to 9,000 after 5 years, so you probably don't have to go too far on the x-axis. I'm going to divide by 16,000 first, so I have 0.5 equal to 0.9 to the x. Graphing this is going to be a lot easier. If you graph this on your calculator, 0.9 to the 0 is 1. So you're going to have 1 up here. 0.5 is right there. It's going to come down like this. And that intersection point, if I check my calculator, happens right at x equals 6.579. Another way to do this is you could use logs. If you really like logs, you could do log 0.9, base 0.9 of 0.5 would be equal to x, right? That's, you had me last year, it's called an unbump, right? We are unbumping the log, and that'll give you the same thing, right? It'll give you the 6.579, but you can always use your calculator, so graphing, I think, is a great way to go. But if you like logs, that's also just fine. So 6.579, and what do they ask exactly? Calculate after how many years the value of the car falls below half its original value. So I would say between year 6 and year 7, but it is less than half by year 7, something like that. Usually they're much clearer, right? Like in what year is the car worth less than half its value, something like that, and then it would have to be 7. So for D, now they're going to tell us how much he sells the car for. So he sells it for $4,000 after 9 years. What is the rate of depreciation? A couple ways to do this. The way that makes sense kind of in my head is I would do 4,000 equals 16,000 times r to the t or x or whatever you want. And then we're going to solve for r. Sorry, not x. We know that. X is 9. Another way you could do it, sometimes you'll see 1 minus r in there because that kind of goes back to the idea that it's depreciating by 10 years, or 10%, excuse me, and then we have the 0.9 in there. I like to just do the r, and then we can calculate the like the depreciation value by subtracting from 1 later, but whatever works for you. So I'm going to divide by 16,000, that'll be 0.25 equal to r to the 9th. Then we can do the 1/9 power on both sides, or the 9th root, whatever makes more sense to you. And we get r is equal to, it's going to be about 0.857. So it doesn't do quite as well as he thought, because he thought it was only depreciating 10% every year. But if we do 1 minus 0.857, oops, that was terrible. Let me make that better. I know my handwriting is horrible. I apologize. If you can't understand anything, just let me know. And that's going to give me 0.143, which is 14.3%. So it depreciated a little bit faster than he thought it would. Right? Thought it was going to be 10%, but it ended up being 14.3. All right, most geometric sequence problems kind of follow this idea, right? You have your first term, you have a rate raised to some power. Even compound interest kind of looks like this, which we're going to talk about in a video in just a little bit. But this is kind of the heart of geometric sequences, right? Is just using this formula right here, the u1 times r to the n minus 1, or if you're dealing with like depreciation, you might have it just to the nth power. But just always think about it like after 1 year, after 2 years, plug a few numbers in and see that your formula is working correctly. So now we're going to try to find some kind of a sum formula where we're adding formulas together. And I have to go to another document for that. I believe it's